Today let's discuss the basics of abstract syntax definition. In particular, I will focus on tree-based abstract syntax. So here's a simple example. So we deal with a simple expression language in which we can express things like conditionals, if true, then 0, else like 0. And so this is the textual representation that would be defined by a concrete syntax definition, which is not the topic of today. And then we also have a tree-based view on the same expression, where the nodes correspond to the constructs and the branches correspond to the arguments of the construct. So here's a truly tree-based representation. On the right we have a term-based representation, which however represents exactly the same tree as in the middle. That sort of abstract syntactical representations are relevant in programming language theory, where we need to define semantics of language elements or programs. We also need to deal with abstract syntax in metaprogramming when we want to manipulate object programs, and thus we have to represent them probably on the grounds of abstract syntax. So here's how we actually define the abstract syntax of a language. So we might use what's called an algebraic signature, which breaks down into many symbol declarations like true, false, zero, suck, predis, zero, and if. And these symbol declarations have argument sorts between 0 and a number of argument sorts, and they have a result sort. So this true here, this is a constant symbol because it doesn't have any argument sorts. And for example, this if here, it has 3 argument positions. They are all of type expr. So in this particular signature, we only have one sort, namely expr. And these different arguments correspond to the obvious parameters of a conditional, that is the condition, the then branch, and the else branch. So essentially, we can think of a signature as defining a set of terms. Maybe terms of different sorts. In this particular case, we only have one sort, expr. So more formally, there's the notion of conformance. So we may say that a given term t is of a certain sort S according to a signature sigma if. Well, the signature has a function symbol f that is actually the same symbol as we have in the term t at the top. And the result sort of f, according to sigma, is the sort S. And the arguments of the term at hand are terms of the argument sorts of the symbol f, according to signature sigma. So this is obviously a recursive definition because of the recursive nature of terms. So we can effectively check that a given term conforms to a given signature. So here's a slightly more complex example. We've got the abstract syntax of a simple imperative programming language. So we've got statements and expressions. We've also got strings and integers, which we assume to be primitive in our signature notation. So we need strings for variables here and assignments. We need integers here because we have a form of expression for integer constants. Overall, the expression forms are about integer constants, variable access, unary and binary expressions. We don't care here about the actual unary and binary operation symbols. We just leave them out for now. And the statement forms are about the empty statement, assignment, sequential composition, if statement, and while statement. So here we've got a nice example of an abstract syntax which involves several sorts. Now, abstract syntax is really used a lot in metaprogramming. So metaprogramming, that stands for programming where the data is essentially also a program. So we call these programs then metaprograms when they operate on programs. And the language used for writing such metaprograms, that's the meta language, and the programs being manipulated are called the object programs, and their language is called the object language. And we speak of the object program representation in terms of the data structure that is used by the metaprogram to manipulate object programs. And we use the term object language in a very broad sense to include programming languages, specification languages, modeling languages, exchange formats, and so on. So this is how we can represent object programs in Haskell. So we've got algebraic data type constructors for the different expression forms, true, false, 0, suck, pred is 0, and if. And then we can use those constructors in actually building Haskell terms that represent expressions of our object language. In a very similar manner, we can represent object programs in Java. So we use abstract class expr, and we use concrete subclasses for all the different expression forms. Further, we use functional constructors to enable the convenient construction of expressions. And those functional constructors are indeed used down here when we construct a nested object that effectively represents an expression. We may also represent object programs in JSON, as indicated up here. So this means we use effectively a dictionary style notation. And we could even use JSON schema to represent the signature for our expression language in JSON, and thereby also enable conformance checking effectively at the level of JSON. And in the same way, we could also represent object programs in XML and use the XML schema language to represent the signature of expressions and again enable schema-based validation. Before I close, I want to briefly bring up some interesting issue around conformance or abstract syntax definition. So interestingly, we can also define a signature of signatures. So by this, we essentially define a set of terms that represents signatures. So this is a very nice meta problem, which allows us to treat signatures, that is abstract syntax definitions, in pretty much the same way as any other software language. So you see all the symbols here, they correspond to some expressiveness of the signature notation. Maybe we have not seen all the constructs, but you see there is a symbol for representing symbols, and there's a type signature for many declarations. And there's some symbols corresponding to the primitive types that we can use. And there's also some symbols here like star and plus to deal with lists, and so on. So this is a very interesting aspect of software language definition. So that should be enough for an introduction to abstract syntax definition. The code base contains all kinds of examples. In particular, the example language that we exercised here is called BTL, and also the signature notations are fully defined in the code base. The software languages book discusses tree-based abstract syntax in all detail and also in context of metaprogramming, and it of course also discusses quite related subjects such as concrete syntax or graph-based as opposed to tree-based abstract syntax. Thank you.